Okay, just going straight on from a previous session. Now we can actually do the formal proof. I hope to be able to get through it pretty quickly because it'll just be effectively a rehash of what I've previously said. Okay, so we're reducing this problem to this one. Okay, we know that this language is undecidable. So if we can reduce this to this, and we know that that's undecidable, therefore this is undecidable, and that's what we're trying to prove. Right? Okay, so that we've done before. Proof by contradiction, as usual. All these proofs are of that form. So therefore, assume there is the usual mathematical symbol. There is a Turing machine R that decides this. Okay. So now it's this Turing machine R that we will feed into it the encoded description of B that I was mentioning before. Okay, so this Turing machine R, which we assume decides this language. Okay, yeah, it decides that. All right. Okay, now construct a larger Turing machine that will use R as a part, as a component. We've done that kind of thing before as well. Right? And we will construct, so partly proof by construction, we will construct this larger Turing machine S, which has R as a part, as a tool, that S uses R, and the solution, the existence of R, that enables S to be solved. So in that sense, this Turing machine S, or this problem if you like, reduces to this one, this problem, R. Okay, and what are we doing with this? What are we trying to do? Well, we want to have it decide ATM. Okay, now if we can do that, since that's impossible, we have prior knowledge it's impossible, therefore we know that this is undecidable, therefore this is undecidable. Alright, so how to, using R, how to construct a larger Turing machine S, now it's an ordinary Turing machine, right? How to construct S so that it decides this language. Okay? Now how to do it. Now, what's S doing? Well, it's this, right? This is the famous halting problem. In other words, this language, its strings, they're all ordered pairs. The halting problem asks, find a Turing machine, or can you find a Turing machine, we'll call it S, okay? Can you find a Turing machine S that, given any other Turing machine W and a string, any string M, any Turing machine M and a string W, will that machine M, will it halt on, or will it accept this string? Now, we know that's the problem. We put in a language format, then this is a string of the language. Okay, right. So S will be looking at strings of this form in this language. These are strings of that language. If M accepts W. Right. So where M is a Turing machine, an ordinary Turing machine. Okay, and W is a string. Okay, so S, the Turing machine, it'll construct a small machine B from, it'll be an LBA type, and it'll construct it from, so Turing machine S can extract the information of these two things. This machine is string, so it extracts from this input M, the information concerning M and W in the way, well, described. Glossing over it, as described in the proof idea sessions. Okay. Okay. So now we have a description of B that that we encode, so angular brackets, and we run R that we assume to exist that decides this language, and this is just a string of that language. Okay, this is just just a string of this language here, and this Turing machine R will return. You just run it on this, and it'll return accept or reject. Okay. Now, given the way B is set up, we talked about this before. But so if R rejects, well, that you want S to accept, for the reasons we talked about earlier. Okay. Because remember that the language that B, I don't want to go into this too long. I already spent a lot of time on it. The language that B's language, L of B, has at most one string, one member. Okay, and from that, the logical reasoning we had before. So if R rejects, then S accepts, and if R accepts, then S rejects. So S does the opposite of what R does. Well, that means for whatever the string is, S is either accepting or rejecting. Okay, and by definition, that means that S here is a decider, because it's never looping. Right? It's either accepting or rejecting. It's actually making a decision on that ordered pair. It's making a decision whether this machine M accepts W. Okay. And that means for all possible ordered pairs like this, which are members of this language, it means that that language is decidable, right? And there's our contradiction. So if we conclude that that's decidable, that's the contradiction. So we go back to the beginning, we negate what we started with, which was the negation of ELBA being undecidable. So if we negate that, then ELBA is undecidable. Hold on. No, go back and negate what we assumed, which was ELBA is decidable, and therefore it's undecidable. Right. A bit of comment here. Now, if R accepts this encoded description of B, now what does that mean? Now, what's R doing? It's deciding on this.